let's see the undecidable, okay, undecidable problem. That is nothing but unsolvable problem. In normal term, what we can say, that is unsolvable problem. We cannot solve that problem. So first one is decidable language. What is decidable language? A language is a is decidable if there is a Turing machine. When the Turing machine is there, a is a decidable. Okay, and decider that accept the language a and halts on every input string. Okay, and it halts on every input string. Like this is a Turing machine M. Okay, this box, sorry, this box is a Turing machine. Okay, and here this is one state and it is going to the final state here, and here a. Okay, so if it is decider for a, decider for like a language a is decidable, it is going to be decidable if there is a Turing machine. Yes, I have a Turing machine that accept the language a and halts on every input string, even if it is yes or we'll change the color. Yes means accept or reject with the help of Turing machine a. A is a decidable. So like this we can make a decidable. Okay, next, a computational problem is decidable if the corresponding language is decidable. We also say that the problem is solvable. Decidable is nothing but is a solvable. Whatever the problem we have, we are solving with the help of anything. Okay, a computational problem is decidable if the corresponding language is decidable. Okay, next, like if I have a problem, does DFA, deterministic finite automata, M accept the empty language L of M is equals to phi. Okay, so if my language is there that is empty, so what is this? So empty DFA is M. M is a DFA that accept empty language. Yes, what is this M? M will accept only the empty language. Description of this M is description of DFA M as a string. For example, we can represent M as a binary string as we did for Turing machine. So here we can represent M. Okay, we can represent M as a binary string as we did for Turing machine. Okay, okay, next, empty DFA, decider for. Okay, on input is M, determine whether there is a path from the initial state to any accepting state. Okay, we need to check the path is there or not from the initial stage or not, because when it is empty, so there should not be a initial and final. So like what here, it is going from here to some final state, that means it is not a empty, does not belongs to phi. When we don't have the state diagram, nothing we have, then that is a accept. Okay, and this is a reject in a simple words. When we have a empty, there should not be a anything, but if we have something, then L of M does not belongs to phi, then it is rejected. What is the decision? Rejected. And if M, L of M is belongs to, sorry, M of L of M is equals to phi, then it is accepted. Okay, because here we need to check what we had the problem, we the problem is L of M equal to 5. If it is satisfied, then our string is accepted. So here L of M is equals to 5. So if we don't have anything the empty, then it will become a accept string, and this is not accept, this is reject. Okay. Okay, so this is about the like decidable. Whatever the decidable, with the help of Turing machine we will get the solvable problem. If we have the empty data, like we have taken the example of this, and we got the answer accept or reject. Okay, undecidable language. What is undecidable language? Not decidable language or unsolvable problem. So there is no decider. In this there is no decider. There is no Turing machine which accept the language and make a decision or halts for every input string. Previously in the decidable, we had the decider. With the help of decider, it's taking the decision or it is doing the halt during every symbol. So but here there is no decider and there is no Turing machine which accept the language and make a decision for every input. So machine may make decision for some input string. So this is called undecidable string. For an undecidable language, the corresponding problem is unsolvable or undecidable. There is no Turing machine algorithm that gives an answer yes or no for every input instance. Like how we were getting the answer yes or no with the help of Turing machine, and we have some decider. With the help of decider we were getting the decision, we were getting the answer yes or no. Okay, or it will halt. But in the undecidable language we don't have Turing machine. Okay, because of that there will be no answer like yes or no for every instance. Answer may be given for some input instance. Whatever the input are there, it will give some input instance. Whatever the input you are going to give, based on that maybe it will give some output or answer. Here we have shown before that there are undecidable language. L is Turing acceptable and undecidable. Okay, means decidable means all complete with the help of decider. Okay, like example A, we have done like PDA. Okay, like PDA, Turing machine, finite automata, that all are decidable. Turing acceptable means with the help of, like this is we can say undecidable. Okay, this is we can say undecidable. So this is a graph and in the middle again it will be like this, finite state machine, PDA, Turing machine, then Turing acceptable. Already I shown you this kind of diagram in previous videos. Go and watch the videos. Okay, so Turing acceptable is undecidable. We will prove that two particular problem are unsolvable. Okay, the two particular problems are unsolvable. First one is membership problem, second one is halting problem. Membership problem and halting problem. Let's see this. In the membership problem, input is Turing machine, okay, is M, string is W. So question is, does M accept W? W belongs to L of M. W belongs to L of M. This we need to see. So what is this? ATM means a Turing machine is M comma W. M is a Turing machine that accepts string W. What is this? MW? M is a Turing machine that accepts string W. Okay. Now, a Turing machine is decidable. The membership problem is unsolvable. Membership problem is unsolvable. Proof. The basic idea, we will assume that a Turing machine is decidable. We will then prove that every decidable language is a Turing acceptable. Every decidable language is Turing acceptable. Okay, so whatever the decidable, that is Turing acceptable. This is a contradiction. Okay, so this is, we will assume that AT is a decidable. We will then prove that every decidable language is Turing acceptable. Okay, the first one, suppose that ATM is decidable. Okay, input string is M comma W, M and W. Okay, and this is a halting decider for ATM, that is H. Yes or no? M accept W or M reject W. Okay, with the help of decider ATM, we are taking decider, then only we will get the yes or no. Without taking the decider, we will not get yes or no. Okay, fine. So this is input string. M W is giving the input, and with the help of this we are getting the M accept W or M reject W. But for this, decider should be there. Okay, now let L be a Turing recognizable language. Let ML be the Turing machine that accept L. Okay, first one is L be a Turing recognizable language. Second one is let M of L be the Turing machine that accept L. We will prove that L is also decidable. We can prove that L is also decidable. We will build a decider for L. When we have a decider, we can prove it is decidable. Okay, if we build a decider, then definitely you will your problem will go under in decidable. Okay, next problem is halting problem. In the halting problem, Turing machine M is string W. Okay, so here the question is, does M halt while processing input string W? This is a question. Does M halt while processing input string W? Corresponding halt TM is M comma W. M is a Turing machine that halts on input string W. Okay, what was the problem in the previous one? Membership. M is a Turing machine that accepts string W. Here the problem is accepting the string. Here it's halt. Okay, M is a Turing machine that halts on input string W. Okay, let's see. Theorem: halt TM is decidable. The halting problem is unsolvable. The halting problem is unsolvable. The basic idea to prove this, okay, basic idea to prove this, suppose that halt TM is decidable, we will prove that every decidable language is also a Turing acceptable. Same as membership problem. Okay. Now suppose that halt TM is decidable. Okay, that means it is a solvable. Input string MW, M and W, decider for halt TM, yes or no. M halts on input W, M does not halts on input W. So with the help of decider, we will get the output yes or no. And here, if it is yes, then it will accept. If it is no, it will not accept. Okay, fine. Next, let L be a Turing acceptable language. Let ML be the Turing machine that accepts L. We will prove that L is also a decidable, so we will build a decider for L. Okay, we will build a decider for L. So here how we are decider for L, just see. Here input string decider for halt ML, ML halt. ML is a Turing machine for the language L, Turing machine for accepting the L, halts on S. Okay, when the input string is there, S. If no, reject S and halt. Okay, yes, then go to the run with input ML, run machine Turing machine with input S, with input S. Okay, here after that ML halts and accept S and halt, ML halts and reject S and halt. Okay, this is the two thing. First, directly, if it is not halt the S, directly it will reject. If here it halts the S, then yes, then it will move to the next. Then run Turing machine with the input S. If it is accept, okay, halt and accept, then that is a accept the thing. And if it is halt and reject, the data is reject. Okay, so this is a decider for L language. Okay, fine. So here L is a decidable since L is chosen arbitrary. Every Turing acceptable language is decidable. Remember this. Turing machine is different. Turing acceptable language is decidable. But there is a Turing acceptable language which is undecidable. Which is undecidable. If we see this graph, this circle, Turing machine is, as we are telling, this is unacceptable, but here that is a contradiction. Okay, but there is a Turing acceptable language which is undecidable. But here what we are telling, Turing acceptable language is decidable. We are telling the both thing, it's depend on the problem, and sometime Turing machine is, most of the time Turing acceptable language is undecidable, and Turing acceptable language is decidable chosen arbitrary. Okay, so this is about the today's lecture. This is a basic introduction of decidable and undecidable problem. Okay, so I hope okay. So in the next class we are going to see the next topic in unit 5, undecidability. Okay, so thank you very much. We'll see you in the next class.